Thank you, Harry. Good afternoon, everyone. It's a pleasure to be here to talk about my research. The focus of my research is to understand different quantum systems and then apply them for the advancement of various quantum technologies. So we know quantum systems are very fragile. Quantum coherence can be easily destroyed by the environment perturbation and thermal fluctuation. So it is therefore very important to isolate a quantum system and then cool down them to very low temperature in order to observe very interesting quantum phenomena. So an important approach is to use lasers to cool down and manipulate very small particles, such as atoms and molecules. And this is the field of ultracold quantum gases. This figure here illustrates the evolution of a system as the temperature decreases. At very high temperature, the atoms behave like classical particles. At lower temperature, each of the atoms becomes a small wave packet. And as the temperature is decreased further, these wave packets will start to overlap and then interfere with each other. And eventually at t equal to 0, only a giant amount of wave will exist. This is the Bose-Einstein condensation. Bose-Einstein condensation means that all the atoms have condensed to the single quantum state here. The other types of quantum particles, fermions. So at 0 temperature, the fermionic particles will occupy the first few lowest energy levels up to a certain energy, the Fermi energy. So one of my main research focus is to understand the properties of Bose-Einstein condensate and the degenerate Fermi gas. Ultracold quantum gases is a very clean quantum system. There's no disorder, and many system parameters can be easily tuned in the experiment. For example, by the interference of several laser beams, we can create a periodical optical lattice potential and put the atoms or molecules into the lattice. This system is very helpful for us to understand very complicated quantum materials. For example, the high temperature superconductivity and many other condensed matter phenomena. We can also use this system to generate entangled quantum states. For example, the spin squeezed quantum states. The quantum fluctuation along one direction is, how do I hide this? Okay, so the quantum fluctuation along one direction is significantly reduced. This is useful for quantum metrology and quantum precision measurements. So there are many other practical applications with ultracold atoms and molecules. For example, we can use them to make atomic chips. We can create a cold atom gravimeter and a cold atom gyroscope to measure very weak gravity and also rotation. People, actually our current time and frequency standard is using the cold atoms. People are now engineering the next generation of optical lattice clocks. The precision of the new clock will be several orders better, and this will allow us to measure the gravitational waves and the dark matters. The other main research focus is the topological condensed matter physics. In mathematics, topology are properties of an object that do not change under continuous deformation. For example, a coil toy is topologically equivalent to a sphere. There is no hole in this object, while a mug is topologically equivalent to a donut. There is only one hole in this object. In solid-state physics, electrons can be in similar torus states, which are called topological states. These systems are characterized by a certain number of holes. We call them topological invariants. A small perturbation to the system will not change these topological properties unless the change is dramatic. So let me give you an example to demonstrate the interesting aspect of a topological quantum system. We know that insulators have a conduction band and a valence band. They are separated by a finite energy gap. While vacuum is also an insulator. The difference between vacuum and a regular insulator is that the energy gap has different magnitude. But they are topologically equivalent. We can continuously evolve from the vacuum into this regular insulator without any big change. Therefore, at the interface between the vacuum and the ordinary insulator, there is no special property. Well, people found that there are some other types of insulators which are topologically different from the vacuum. So you cannot evolve from the vacuum to this topological insulator without any big change. There must be some defect at the boundary. This is manifested as the appearance of an edge state on the boundary. Topological insulators are completely new quantum materials. It is insulating in the bulk, but conducting on the boundary. The conducting edge state will add a new energy dispersion in the gap of the bulk energy spectrum. The most interesting phenomenon about the topological system is that the edge states are topologically protected. It moves from one direction to the other direction. If you add some defects to the interface, then the edge state will just move around the defect and then continue its propagation. So my research focus along this direction is to explore topological phenomena in various systems, including electronic, atomic, and also photonic materials. The ultimate goal of this direction is to use these topological properties to engineer new functional quantum devices, and also for topological quantum computation. So in conventional quantum computing protocols, quantum errors cannot be avoided, as shown here. In the calculation, a qubit can somehow change to a different qubit. We may need millions of additional qubits to correct this kind of error. While for topological qubits, they are topologically protected. Topological quantum computers are therefore intrinsically stable. So right now, Microsoft is developing a topological quantum computer. Okay, so to wrap up, my research focuses on these three different aspects. From the fundamental point of view, we studied the interaction between lasers and atoms and molecules, solid-state materials, in order to engineer new quantum systems. We then studied the many-body quantum phenomena and also topological phenomena in these engineered quantum systems. Finally, we try to find the applications for quantum computing, quantum metrology, quantum simulation, and also quantum information. All right, so this is a brief introduction to my research. I'll be happy to answer your question